Hey guys, Dr. Mike Israel here for Renaissance Periodization, RP Plus, and RP University. Lecture number 7 in the Training Principles course is the principle of phase potentiation. Ooh, this is one of the fancy ones. What's on the menu for today? We're going to go give a simple definition so you guys know where we're going with all of this. We're going to do an analogy for phase potentiation that really isn't even an analogy. It's more specific than that. It's an example of how this principle works in a non-biological, simpler system so that you can always have a really awesome, easy, super simple example to take with you when you think about phase potentiation. Because it could get really confusing if we just keep it to what its actual applications are. But this example kind of analogy is going to make things super, super clear. It's always helped me a lot. After that, we'll cover the technical definition. We'll talk about a sub-principle called adaptation decay of phase potentiation that is a big part of what that phase potentiation is. We'll talk a little bit about sample decay rates, and it really an extension of that sub-principle talk, examples of application, and programming implications. Lots to chat about. So the simple definition of phase potentiation is that when you want to get better at something, you essentially build up what supports that something first before focusing on it specifically so you can get better long-term results. Just like not eating for a couple of hours potentiates the culinary experience you're going to have at a restaurant later that's really good, because when you're hungrier you can taste food better, as opposed to just eating a crap load of food before you go out to eat, and then you go out to eat, you're like, I'm not really hungry, nothing really tastes that great. So we could say that not eating before going out to a fancy restaurant can potentiate your culinary experience of the food. It makes it better. One thing done earlier makes the next thing go better. And if we can sequence several things like that, we have a chain of events, one potentiating the next. If at the end of that link of events we have higher level of sport performance, boy, we're onto something, because then we can sequence training in a way that makes every part of it better because of its logical location, because one thing makes the next better, makes the next better, makes the next better. So we examine what to do with training. We got to look at that bottom rung first and say, okay, what supports all of this, and what do we put on top of it? To take that particular analogy, or rather really example, is what I like to call the skyscraper analogy for phase potentiation. Question: how do you build the tallest skyscraper? Let's say that was your goal. It's been many people's goals over history. How do we build the tallest possible skyscraper? Well, if you give this job to a toddler, say maybe a 4-year-old even, or a 6-year-old, and you ask them, how do you build the tallest building? What do you do first? The young child will almost invariably say you go up, and you go as high as you can. And if you gave him a bunch of blocks to play with that looked like various parts of a skyscraper, he'd probably pick the spire, the part of the skyscraper at the top that maybe has like TV antennas on it. He'd pick the spire first and go boom, and that's what he'd put down because it's already the tallest part. He'd be like, there we go, good start. But anyone familiar with engineering remotely knows that that's actually not the correct answer as to how to build the tallest possible skyscraper. If you want to build one, the first direction you start building in is down. What? That's right. Anytime you have a really tall building going up, one of the ways you know or get a hint that it's a tall building, if you're walking around a major city and you see a construction site and you want to know how tall the building's going to be, look at the construction site before the building's even gone up. If the hole they're digging is super wide and super deep, they're going to lay down a huge base. The base of the skyscraper, which houses parking structures, elevators, all sorts of life support systems, air conditioning, electricity, etc., if you have to make a big deal of room for that, you know you're making room for something really special after the first floor clears the foundation. So first you build the base, then you build the main floors, and lastly, you put on the spire, right? Why? Well, because the bigger the base, the more floors you can hold. The more regular floors there are, the higher up the spire can start. Because remember, if you just put a spire down, first of all, it's not really a skyscraper. It can't hold anything. People can't work and live and play in a spire, okay? And also, if you build something super thin all the way up, you can do that. And then it's like a TV antenna. It's got to be anchored from every single side by huge cables because it just tips over in the wind. And yeah, it's going to be super tall, but more or less functionless compared to a skyscraper, which does the TV antenna part just as well as a TV antenna, but does everything else. It actually has all the stuff in it. Once you get the floors, you can put the spire up even higher on top of them, right? So if you begin kind of like the 4-year-old did and begin construction by putting the spire down first, you're not going to go very far and you're not going to build the tallest building. And the most important part about this analogy, or rather example, is that the order in which you build the sections, base, floors, and spire matters a ton. Because while a big base potentiates how many floors you have above it, it doesn't directly potentiate the spire. If you want to stick a spire into the ground and just go 200 feet up and just leave it there, do you need a huge base? No, it's a total waste of your time. As a matter of fact, it's even more telling than that. If you want to stick a spire into the ground, you're going to be sticking it into the base, which is going to be lower than the ground. So you're going to be missing 10 floors all of a sudden. It's going to be even worse. So because the base only potentiates floor building, and floor building only potentiates spire construction, and spire construction is relatively useless without those two things before it, we have a logical structure of skyscraper design in which one phase potentiates the next. It improves the performance of the next. It improves the overall outcome by that method. Just the same way with training, one phase is going to improve the next, to lead us to an end result that we like the best. So the technical definition from that derivative is, here it is, training should be arranged in a logical sequence of phases, whereby the initial phases potentiate the improvements that can be made in the later phases, improving the rate of gains for the whole process above and beyond what would be possible if all abilities were trained concurrently at the same time, so to speak. So if we built everything all at once, right, we built kind of like some kind of structure that was pretty solid. It had like its own little kind of base, like it was wide to begin with, and it had like some floors, but the floors didn't have much in them. The floors are really super thin, so they kind of look like a spire. We'd get up pretty far, but we wouldn't get up as far as if we built a distinct base, distinct floors, and a distinct spire, right? Remember, phase potentiation, it's one of those situations where the later training principles really draw on the first ones. You could almost say they're derivative of the first training principles. So phase potentiation makes use of a couple of really obvious training principles early. It makes use of specificity and training modality compatibility because we're saying, look, the best way to establish a fitness quality is kind of by itself, and then later we're going to stack stuff on top of it. To use a really easy sport example, we want big muscles so we can make them stronger. But the kind of training we do for hypertrophy doesn't train the nervous system super well for strength. And if we were to do strength training, it's not sufficient volume to really get good hypertrophy. So we're admitting that there is not perfect compatibility between training styles, and we're going to use specificity to first establish a good deal of one training ability, and then build on top of it with another, thus never violating specificity. In addition, the phase potentiation principle makes use of directed variation. When we're varying, when we go from hypertrophy to strength, we are not varying at random. We didn't go from hypertrophy to work capacity. We went hypertrophy to strength because every training phase is purposeful and not just different for its own sake. It's hypertrophy to strength. It's not the other way around, and it's not some random assortment. So yes, variation is a super important part of phase potentiation. It's really very much an extension of variation, but it is a very special case of the directed adaptation subprinciple, you could say. And lastly, and very importantly, phase potentiation makes use of a subprinciple called adaptation decay. Adaptation decay is so important, it has to be a subprinciple, and we have to talk about it next to really, really describe how phase potentiation is designed, but also how it's limited, right? So the subprinciple is adaptation decay, and here's kind of the story. If you're going to build a skyscraper and you run out of funds, like you run out of money to pay for it midway through, let's say you've got the base built, but you haven't put any floors on it. The question is, How long can you let the base sit there? Maybe you can cover it up with a big tarp until we can't guarantee its structural integrity. And this happens with buildings all the time. So sometimes buildings will start being built and then the bank has trouble, or maybe the war starts, a country goes into a depression, building stops for a while. What they can do is they can kind of mothball stuff, and for several years they can just leave it. And when they come back, they can clean everything up and start building again. That happened all the time. The thing is, what is the decay rate of the base in a real, actual, literal, technical decay? If we come back 100 years later after the base construction, can we be sure that it's ready to accept floors? No, it's probably degraded to some large extent. Bugs might have eaten the wooden parts of it, right? The various other heavier concrete parts might have sunk into the sands in various ways. There might have been some shift in the base. Various metal components could have rusted and no longer support the weight they were supposed to. So we can't just assume that the base is going to last forever. So if we're going to sequence floors on top of a base, we had better know how long that base is good for. And if we're going to come back later and try to build on top of it, we want to know its decay rate. If it's on the order of centuries, we don't have much to worry about. If it's on the order of decades, we got to be something to worry about. If it's on the order of years, well, gee, we got to build the whole thing right away, right? Exact analogy to that is, if you're taking strong muscles and making them fast, remember, then we're applying speed training, which has some modality incompatibility to strength training. So we're doing mostly speed training. How long can your muscles stay strong enough to support speed, but while only receiving speed training? That's the question. Right? So just like how long can we expect the base to hold stable for the floors, we can say, okay, if strength is what we're basing our speed on, but once we switch to speed training to milk that last little bit out of our abilities in speed, are we so sure that strength is going to hang around? And the next question is, how long? Right? Because that tells us a lot about how long we can expect to get faster. And here's the deal. Because different underlying characteristics on which latter abilities are based have certain decay rates, we have two implications we can draw from that. We must do a couple of things. First of all, we can't exceed the decay rates when selecting total macrocycle length. So example here is we've got to begin fixing the skyscraper when the older base starts to wear down, not just when the newer spire starts to rust. So let's say the base starts to wear down after 20 years, but the spire was only, and so does the spire. We'll make this simple. Every part of that building starts to wear down 20 years after initial construction and requires us to do something about it, maybe make some improvements to it, or at least an inspection. And let's say the skyscraper took 10 years to build. We finished the spire 10 years ago, but we finished the base 20 years ago. So 10 years after the skyscraper has finished construction, we can't look at the spire and go, so everything takes 20 years to start to degrade. We built the skyscraper finished 10 years ago. We're good. The spire's 10 years old, we're good. But hold on, the floors might be 15 years old, still fine, but the base might already be 20 years old. So we have to look at even the earliest fitness characteristics that we've established and make sure that their decay rates support the next one, and support the next one, and support the next one. There can't be any broken links in the chain. Because if something you've established midway through or at the beginning of your logical sequence of your phase potentiated plan is already beginning to decay significantly when you're building the later components or expecting high performances, you're in a world of trouble because your very foundation for those high performances is starting to crumble on you and your performances will degrade. Now, we may just not want to exceed those total rates, right? So we may say, okay, if we're establishing some kind of base and we need to perform at a high level in 6 months, nothing in this macro cycle can be a 6-month meaningful degradation decay rate. It has to be longer than that. There's another option. What we can do is periodically reestablish these underlying characteristics, go back and train them up a little bit, kind of like fixing up the base of the floors to give them a little bit more time to hang around if we plan to exceed the limits set in point A. So if we say, okay, 6 months is when we need to perform 6 months from now, so everything we establish has to hang in there for 6 months. If we have to perform 8 months from now, whatever it is that degrades within 6 to 8 months, we have to come back at some point, within 6 months of when we're going to be performing, and kind of retrain it, reapply it, put some, so sort of kind of fix it up a little bit, and come back and train it to reestablish that quality to make sure that the degradation doesn't occur on a net level and actually impact performance at the end of the day, right? So we can enjoy the fuller effect for longer and get everything done that we need to. So the chart you're looking at now is a chart of sample decay rates for kind of intermediate advanced collegiate athletes. They're super rough averages, so don't take these too much to heart. They're more like examples and really rough guides for program design. Let's go through how to read this chart and just give you an example, and you can read it on your own much more extensively just by pausing the video, for example. So when you're training for something, that's the top situation that we have there, the top axis. And then on the left is what effect that has on your various abilities. So if you train, for example, for size, what is the effect on your size? Well, training for size increases your size in the long term. If you're training for size, and remember, you're relatively advanced, what effect does that have on your strength? There's actually a slight decay within 2 to 4 weeks of your maximal strength. Why? Because size trains different aspects of your nervous system. It teaches you, size training usually occurs in rep ranges that reward a little bit more of a muscular endurance style ability and not peak nervous system application. So it's a slight decay and then it just kind of stabilizes. If you train for size, what is the effect on your maximum ability to produce power? Well, remember, power rewards explosive qualities of the nervous system. They change really rapidly. Power will decay within 1 week of dedicated size training. So if you want to be the most powerful person, you want to high jump the highest, don't do sets of 10 the week before your competition. You're not going to do so well. And if you're training for size, what effect does that have on your speed? Remember, speed is an incredibly fatigue-sensitive ability, and it's incredibly sensitive to particulars of the nervous system. Very specific techniques, very specific modes of action, highly explosive ones. Basically, after your first leg workout, for size, you will get slower. Maybe not markedly, but it sure will show very soon. So there's an immediate beginning in decay. So if you want to arrange your training properly, make sure that you look at charts like this one and see what decays when, to inform you about how to peak and taper for stuff, and also to inform you how to create your phases. So, for example, here's a really interesting one. If we're training for strength, what effect does that have on our muscle size? No change. Strength, to put it another way, strength training conserves our current levels of muscle size. So if we wanted to put a foundation of size training first, how long can we train for strength without that base of size decaying? The answer is forever. So if you want an immediate logical sequence in phase potentiation, possibly, is hypertrophy to strength. Because strength benefits from hypertrophy like crazy because you get bigger muscles. Now the strength training teaches the nervous system how to use all those big muscles and make you stronger. And also, because you're training for strength, you never have to worry about your size degrading. It's perfect. All these other ones, they don't work so well. There are decay scenarios, but some of them decay. It says, power training, will lead to a size decay, just training for power, within 2 to 4 months. So we know that, when we finish our strength phase, if we're entering a power training phase, within 2 to 4 months, we can expect for our size to start to decay. Then what does that mean? Our size will decay, then our strength begins to decay. That's not great. What happens when our strength begins to decay? Well, the primary underlying characteristic of power, which is force production, also begins to decay. That's really bad. And that's what that means, that power will start to degrade size within 2 to 4 months, which really means, and we can scroll down, and says, if you're training for power, what is the effect, only power, what is the effect on your ability to produce power as a higher level athlete? Well, it increases it for a while because it teaches your nervous system to do cool stuff, but notice that within 4 to 6 months, there's a decay afterwards. Why the decay? Because within 2 to 4 months, your size starts to be harmed. Within 3 to 5 months, your strength starts to follow, clearly because nervous system abilities can only do so much with size. And then in 4 to 6 months, you start to experience a decay. So if you're a well-muscled athlete, and you only train in power, which means very low volumes of high force training and very low volumes of explosive high speed training in conjunction within the same microcycle, If you train like that for like half a year, you're actually going to start to decrease in power. Then what do you have to do? Come back and reestablish the size you lost, reestablish the strength gained from that size, go back again. So the real kind of inference here is that a power phase in a phase potentiated sequence probably shouldn't last longer than half a year and might be better off lasting only several months. Perfect use of that chart right there. So let's get into some examples of application. Well, the proper examples are all over sport training. For example, some classic phase potentiation or periodization models. A work capacity phase in sport, into a strength phase, into a power phase, and into a speed phase, used in tons of team sports and speed sports all the time. Classic hypertrophy, strength, and peaking for powerlifting and for weightlifting. Then we have basics phase for technique periodization, kind of learning a basic move, taking the move and putting into a combination of effective moves once it's learned well. And once those combos are learned well, take it into a live training phase where you use combos in an actual live setting. Very good phase potentiated periodization. And then in endurance athletics, we have a work capacity phase, and then a kind of a lactate threshold phase, and then a competition pace phase, each one potentiating performance in the next. Now, what does over-application of phase potentiation look like? How we do take this too far? Here's how we take it too far. You start to see these phases in complete isolation. You start to say, okay, specificity is super important. Training modality compatibility is super important. So every phase has to have its distinct goals to get as good at that phase as possible before going on to the next one. We're overvaluing potentiation and kind of undervaluing sort of a generality of training that we can't, we're sort of violating specificity by going too far away into that specific phase's demands while missing the specificity of the sport in general. So for example, if you are doing a powerlifting hypertrophy phase and you do only sets of 10 or more, and you only do machine lifts, the transfer into the strength phase is going to be a disaster because you're going to be, instead of doing sets of 6 to 10 reps, which has a pretty good hypertrophic effect, but a pretty good nervous system similarity to strength, you're going to be so dissimilar, it's going to take you a strength phase just to get used to sets of 5 again. And because you've gotten bigger on machine lifts, the specificity of that, yeah, you're going to have big muscles, but they're not going to be developed in the specific areas that we want them to be if you had done it with barbell lift derivatives very close to low bar squatting and bench pressing and deadlifting. So we've essentially moved really far into hypertrophy. Great, we've got a ton of size, but we didn't worry enough about that size's ability to transfer to the next phase. So we've kind of given phase potentiation too much credit. We say, if we train, people don't believe in phase potentiation, say you need to train for the same stuff all the time. It's always specificity and it's always only the sport. But it turns out you need to train for completely different stuff and you just sequence it right, it works. Yeah, but it's not completely different stuff. It still has to be very much related. On the other hand, if you're really paranoid about getting away from training what you want to train, you can under-apply phase potentiation and think that qualities degrade immediately and that there's no delay in degradation, that decay happens really fast, and you think we always need to support all qualities and stay specific. So what do you end up doing? Well, in powerlifting, you train for sets of 15, sets of 6, and sets of heavy doubles all in the same week, every single week. Why have phases of hypertrophy? Why have phases of strength? Why have phases of peaking? We can do everything in the same week and just keep getting better. The problem is, it doesn't work that way. Remember our concurrent skyscraper that's kind of got a sort of base to its structure and it's made of floors, but they're really skinny floors, so it kind of looks like a spire. It's going to go up high, it's going to work, but not as well as if we have a phasic structure where the phases are distinct. They're not so distinct that we've forgotten the rest of it. That would be the over-application, but they're distinct enough to make a big difference and give their individual contributions to the whole, right? So lastly, let's work out some program design implications. What are some big lessons to learn here? Well, here they are. Before, and this goes back to Dr. Hoffman's talks about making sure that you really, really get a needs analysis going. We don't just jump into training, we find out what we need. One of those things is always find out what the underlying systems are of an ability and which ones are the biggest contributors to that ability's performance. That tells you what you need to work on, probably first, and certainly as part of the phasic structure. So for example, power is generating force at high velocities. It's very explosive. Let's say putting a shot. If you look at a shot putter and you only know the specificity principle, what are you going to have them do as far as training for shot put? Well, they're going to shot put a whole lot, which is a great start. But it turns out the most underlying element of power is strength. Speed can be trained, but very little. It's more perfected than trained. Strength can change wildly. An individual can get twice as strong, but can they move their hand twice as fast, even without a load? No way. We're talking about several percent increase at best with really good training. So the most changeable, malleable, and thus valuable characteristic underlying power is strength. So when you see a shot putter and you know phase potentiation, you don't automatically think we're going to train him only in the shot put. Yes, shot put training is very important, especially a lot of it is important towards the end of a macro cycle where they're going to compete. Remember, specificity, we do more things that are related towards the end before competition. But maybe earlier in the phases of training, you're going to want to make that person really strong. Why? Because you know that strength feeds into power a ton. So once you get a shot putter that's incline benching 500 pounds, gee, that's well on his way to having Olympic level shot put performances. But if you've got a shot putter that's plenty fast, but is only incline benching 220 pounds, you got to wonder, maybe improving underlying strength is going to improve power even more than training power directly, and that's absolutely the case. Number 2, you want to know the decay rates of the phases that you're putting in, of the actual adaptations, so that they're accounted for and not leading to net decay, right? Especially during peaking. What does that mean? So we know that training super hard makes fatigue. So we could have this idea that if we don't train hard leading up to a competition, we have very low fatigue and high fitness. But hold on a second. High fitness means we've retained the abilities. If we know something decays really fast, we got to keep training it pretty hard for it not to decay. Here's a really good example. Strength hangs in there for a long time. It doesn't decay very fast at all. It is also incredibly fatiguing. So for powerlifters who are taught to demonstrate strength at their competitions, the commonality for large, strong powerlifters is to basically train almost not at all in that last week. It's more like just going through the motions with super light weights. There's no strength training in the last week of training. Why? Well, 1, because we need to drop that much fatigue, and if we strength train, we wouldn't. But 2, we can afford it, because for 2 or 3 weeks, strength doesn't move anywhere noticeably, and for sure for a week, so it's totally fine. On the other hand, if we're not aware of that decay rates are different, and we come from the sport of powerlifting, and we start applying that to other sports like short distance sprinting, like 100-meter sprint, and we say, all right, fellas, got 100-meter sprint team, train super hard this week, next week's meet week, we're not going to do anything, no sprinting. People are going to get really confused. Sprinting decays within several days of not performing that activity at a relatively high level. So if you took a week off of sprinting, the decay rate's so quick, you would lose a ton of fitness. Now, would you be fatigued? No. Would you be fit? No. Your performance would suffer. So how do you do it with sprinting? Well, with sprinting, you change your volume of sprinting. You certainly reduce your volume of sprinting in the last week, especially in the last several days, but your intensity should stay high all the way up to maybe the day before the event. You should still be sprinting super fast or relatively frequently, because we can't afford to drop sprinting out really far away from the meet. It decays too fast for us to be able to do that. Number 3, remember that we need to keep all the phases in context of the grand scheme. Purely specific phases are rarely needed. When we say phase, we mostly mean that there is an emphasis-de-emphasis towards the desired quality and away from the other qualities. So an athlete, a thrower, for example, may very well train for power and actual do shot put exercises the entire throwing season. But they're going to do not so many of them when they're training mostly for hypertrophy. And they'll do some strength training then too. But in the strength phase, they'll train mostly for strength, not a whole lot for hypertrophy, maybe just a little, and do a little bit more actual throwing. And in their peaking phase, in the power phase, they're going to train a lot for power, pretty much very little hypertrophy training, if any, minimal strength training, and lots of throwing. Notice that none of the qualities we ever really take away. We just emphasize one and de-emphasize another, and then another phase will do this, and then another phase will do that. It's not a complete zero-sum trade-off, right? When you're picking phase lengths, don't make the phases so short that directed adaptation is violated. Okay, if you have a phase that lasts 2 weeks, what the hell are you going to build in 2 weeks? Nothing. Right? Let's say you got a hypertrophy phase that lasts a week. How much muscle are you going to build in a week? That's even a wrong question to ask. How much momentum of muscle gain are you going to generate in a week that you're not just going to lose the next week? A week of muscle gain builds you muscle, but it almost doesn't matter what you do after that week. Nothing's going to retain that muscle for you. You got to build muscle for probably at least a month before any of it will stick around. So definitely don't want to violate directed adaptation. And on the other hand, you don't want to violate variation for how long the phase is. So you say, okay, I'm going to have a hypertrophy phase that's 6 months long, and then a strength phase after that. Well, geez, 6 months, especially for an advanced athlete, 6 months of dedicated hypertrophy, you're getting very little hypertrophy towards the tail end of that. Maybe if you stop the hypertrophy phase at 4 months and start a strength then, it would make more sense. Even if you have the time to run all those phases, a little bit more variation probably helps in the context especially of a more advanced athlete. Now, a lot of these phases can be longer for beginners, but as you get more advanced or intermediate and then advanced, the phases tend to shorten up. How much utility you get out of them, how quickly they start to become stale increases. This is especially true for phases like power and speed development. You only really train speed for weeks until it becomes a relatively useless thing. Your nervous system, your technique peaks out really fast once you're relatively advanced, and unless you come back and build more size or build more strength, or go away from speed training just to do strength training for a while and then come back, go to power training. Speed training doesn't by itself make you faster for very, very long. It's designed like a spire on a skyscraper. It's the tip of the spear. You don't spend most of your time on it because after a while it just doesn't do a whole lot. It's just by nature not very overloading, and that's a big part of the problem. Lastly, for high technique sports, remember taking that lesson of never moving completely away from a general plan, especially for high technique sports in which your ability to crisply execute the techniques needs to always kind of be emphasized. Yes, you're going to go through different phases, but some semblance of full gameplay should likely remain throughout. But back to point number 3, it's maybe 70-30. So for example, if you're training tennis players, yes, there should be phases of training in which you're working on their serves a lot, in which you're working on their backhands and on their forehands, specifically for hours on end in a practice. And they're playing much less actual tennis. But during those phases, they should still play a bit of tennis. Now, maybe they usually play in a peaking phase, in a live phase, getting ready for competition in tennis. They may play 15 hours of tennis a week and do 5 hours of everything else. During a phase in which they're prioritizing individual technique perfection or learning new techniques, maybe they'll do 15 hours of technique work, but 5 hours of actual tennis. Notice it's not 0. You don't want to take tennis players that have not played tennis for a while and just work on individual moves, because the way they synthesize all those moves, those natural movements, chord awareness, that stuff has high decay rates. And if you let it degrade for months, you're going to come back and be rebuilding it for a while before you ever see anything as far as a benefit. So it's all about emphasis, de-emphasis, the kind of that 70-30 rule in general, and not taking things away completely and then replacing them later with other things. Give that some serious deep thought. See you guys next time for the last of the training principles.